Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tier. This is my continuing feature on the Math Lovers book. And for the last week or two, I've been going over different kinds of discrete dynamical systems. This is section 9.1 of chapter 9, which is on dynamical systems and chaos. And there's a particular type of discrete dynamical system known as cellular automata that's been getting a lot of attention, I'd say, for the last 20 or 30 years. And I'm just going to give you a brief overview what those are today, and then we'll get into some different types, but especially Conway's game of life. Anyway, let's begin. So, what is a cellular automata? Well, cellular automata is, like I said, it's a type of dynamical system, but it's a specific type where the things being iterated isn't a number. I think all the answers we've been looking at are discrete dynamical systems involving, you start with a number as a seed, or maybe a number and index or something, and that gives you another seed based on a rule. Well, you don't have to use numbers. You can use patterns. And these can have, any number of dimensions you want. And a cellular automata, I mean, maybe I should just talk about a specific example, Conway's game of life, because that's the most famous one. I'm going to talk about two examples today, really. There's a lot more, but in 1970, there was a very famous mathematician named John Horton Conway who developed, I think it was the first two-dimensional cellular automata, and was called Conway's Game of Life. He hated that name, by the way. I think just because people were talking about it all the time to him, he didn't think it was his greatest accomplishment. He did a lot of pretty other great stuff in math. Um, but anyway, what Conway's Game of Life is, I'm going to go into this much more detail. I think starting in my next lesson on the Math Lovers book. But it's played on a two-dimensional grid, and then you have these cells in this grid. So they're square cells. You just imagine, a infinite grid with, a square lattice, and each cell in this grid is a square, and they're all connected to their nearest neighbors. Every square has 8 nearest neighbors. You count the diagonal neighbors as well. And then each cell can either be living or dead, or you can describe them as being off or on if you like, or black or white. Doesn't really matter. But there's rules for how the cells get turned on or turned off in what's called the next generation. So it keeps evolving. And these live cells, if you want to think of them that way, grow for a while or they can die. The whole pattern could die if you start with an unfortunate configuration. But in general, you end up with some pretty interesting behavior of this thing. And like I said, I'm going to devote several lectures to Conway's Game of Life, so you'll learn all about it from me. But I think the best way to learn about it is to play it yourself. There's plenty of websites out there where you can play or download various versions of Conway's Game of Life, and you can play it to your heart's content. Discover whatever kind of patterns you want. I did a lot. I spent, a lot of time doing this myself, and I loved it. But Conway's Game of Life is just one example of a cellular automata. I mean, like I said, it's probably the most famous example. There's a lot of variations on Conway's Game of Life. You don't have to play it on a rectangular grid. You can play it on a hexagonal or a triangular grid. I even invented a variation myself that played on a Penrose tiling grid. It's not even a periodic grid. It's a quasi-periodic grid, a quasi-lattice. But you can have a lot of fun with it. And you can change the topology too. You can play it on the surface of a torus, or you can play on the surface of a Klein bottle if you want, or the projective plane. Well, those are just two-dimensional cellular automata, and you can change the rules too. The rules aren't fixed in stone, and depending on your rules for how cells multiply or how they die off, you can get different kinds of behavior. And John Horton Conway kind of had to tailor his version pretty delicately. It turns out that you have to be pretty specific about rules that give you interesting behavior, because most rules don't. But anyway, that's just two-dimensional cellular automata. And I think that probably the most famous pioneer of the whole theory of cellular automata is another very famous mathematician named Stephen Wolfram. He's also the founder of Wolfram Research, which I worked at for 3 years, from 2000 to 2003. And he even wrote a book called A New Kind of Science, which is all about cellular automata. And, I think he's a little bit of an egomaniac because he thinks he's the next Isaac Newton, or at least he did when he wrote this book. His claim was that we can kind of rehash science or reformulate science in terms of cellular automata. I don't agree with that. But it is a pretty fascinating book. I have this book at home. I've read the whole book. I read it right after it came out when I was working at Wolfram, which was in 2002. My name's in this book, by the way. I did make a few minor contributions, so my name's in the index. I talked about, I guess I talked about elliptic curves, and a little bit of the history of the solution to elliptic curves, which you can think of as an example of a cellular automata in one way. I can't remember how, but I am referred to on one page of this 1,200-page book. So a little heads up on that. But what else do I want to say? Stephen Wolfram was more interested in one-dimensional cellular automata. Game of Life is a two-dimensional one. The simplest ones are just one-dimensional. So he considered, this was part of his doctoral thesis. He considered one-dimensional cellular automata, two states off or on. They don't have to have two states. As a matter of fact, there was another famous mathematician, John von Neumann, who I think he created one of the first cellular automata in the 1950s, but his had 29 states. And he was trying to use it to prove, the universality of computation, which Alan Turing did as well, using a Turing machine, a very different approach. Um, but anyway, what I guess Stephen Wolfram did when he was a graduate student was he classified all 256 one-dimensional two-state cellular automata with nearest neighbor rules. There's only 256 of them. And what's surprising about this is that you get different kinds of behavior. He classified cellular automata into four types. Class 1, 2, 3, and 4, depending on their behavior. I guess classes 3 and 4 are the most interesting. They kind of, they're classified from most predictable to least predictable. I think class 1 either die off after a finite number of generations or fill the whole region after finite number of generations. And I think, class 2 are a little more complicated. They show some kind of pattern to them, some kind of predictable pattern. I think class 3, they could show predictable pattern, but they don't have to. They kind of become chaotic for a while, but after a while, they all settle down to a predictable pattern. Class 4 is the most interesting because those allow for universal computation, in other words, Turing machines. This has actually been proven. And class 4 are pretty rare. I think only like maybe 8% of all subcellular automata are class 4, but they're very, very interesting because you can use them to compute anything you want. You can do any classical computation you want using a class 4 cellular automata. This is what Stephen Wolfram essentially proved. He didn't prove it, but he kind of laid the groundwork for it. I think later, I think there was a mathematician named Peter Cook who also worked at Wolfram. I didn't meet him when I was there, but he proved, I don't know when he proved this, I think somewhere around the time I was working there, that one of Stephen Wolfram's 256 cellular automata, I think it was one with rule 90, if I'm not mistaken, that one is universal. It can actually compute anything in the world using that very, very simple cellular automata. So anyway, that's all I have to say for today. A little bit of an overview on cellular automata, which I think is a really fascinating kind of new area of math. And the reason it's new, maybe I should just say one more thing about this before I get out. The reason this is a pretty new area of math is you really need to simulate them on a computer. I mean, it's not just to work out the theory on pencil on paper. You actually have to see how these things run. And this had to wait until the computer age. I mean, John Warren Conway invented his game of life in 1970. And, he himself, you kind of simulated on pencil and paper at first. It wasn't until maybe a year or two later that, we started writing computer programs to simulate it. But now they're all simulated on the computer. And they're all pretty neat to watch. And we've learned a lot about behavior. And it's not just a recreation either. They have a lot of important applications in various areas of science. I wouldn't say Stephen Wolfram is the next Isaac Newton, but he might be on par with some other pretty great mathematicians throughout history. Maybe even Rene Descartes. I don't know. I wouldn't even go as far to say he's great as Rene Descartes, but he's probably in the top 100 mathematicians of all time. So if you're listening, Stephen, that's my tribute to you. You're not what I think is the top 100 of all time. I'm not. I've only published 4 math papers in my lifetime. Maybe I'm in the top 1,000, but definitely not on the top 100. But anyway, that completes my video for today on cellular automata. So thank you for watching. Long live math, and I'll see you next time. Bye.